page. Tyler? All right, guys, so our test is on Wednesday, and I intend it's just to do review today. So I'm going to go over all the different types of problems that we'll have, what you can expect. But again, in short, we're doing the very last part of Chapter 4. You have one free response, no multiple choice from Chapter 4 to be a two-body, 2D problem. I'll go over sort of the process for working through those, but it's a lot like what we did before in the previous exam, except we have to resolve our vectors. And then the second part will be Chapter 5 and then Chapter 6. In Chapter 5, you'll have a conservation of energy problem. You'll have a force that varies with position. Don't worry, I'll write all this down. But you'll have a force that varies with position, and you'll need to figure out the work that's done by that force. That means you need to do the integral of the force with respect to the position. And then we'll have the work. You'll have to do a dot product to determine the work of a force as it works over a certain displacement. And you'll have to do, I think that's it. I'll make sure we'll go through it. And then in Chapter 6, you'll have a 2D collision, or you'll have an impulse problem. That's where an object changes its momentum. You need to figure out the force that's involved. That force is delta P over delta T. And I think that's it. Okay, so let's go through. For first, you'll have Chapter 4. I'm going to summarize first, and then we can ask questions if you have particular questions. So you have a two-body, 2D problem. And we've worked through some examples. Like, for example, we worked through one where we had an object like this. This would be a good example of a two-body, 2D problem. You can find examples of these back in the old exams as well. I think I did one time where I had two objects going like this. They were connected by a rope, and they were moving. They had like a force on this one that was moving it to one direction or the other. You could also, what else have we done? I think I've done one before. I'm not sure if I have, but this would be okay too, where I have one like this, and then I have a block up here, and they're traveling downward or to the right. In these, the process is always the same. The way you do these, you draw your coordinate systems on each body. Remember, if it's on an inclined plane, then you want to draw your x-axis along the inclined plane like that. You label your forces. So over here, I'd have force weight. I would have force tension, and that would be it. But you recognize that the tension here is equal to the tension here. So these two are equal. And because it's a two-body problem, you'll have a tension force because they'll be connected by a rod or by a rope or something along those lines. So make sure that you remember that these two forces are going to be the same. Then if you have something that's sitting on a surface, you'll need to include the normal force. Remember, the normal force is perpendicular to the surface. All right, so if it's on an inclined plane, that doesn't mean it's perpendicular to the ground, but to the surface. Remember, that's different. You'll also need to include the weight here. Uh, being very careful that you keep your weights separate because they will be different. Okay? So something along those lines. You also need to figure out what is the acceleration. So is it going down the inclined plane or is it going up the inclined plane? And usually I'll tell you that if it's going up or down the inclined plane. Over here you have something similar. So also don't forget on our inclined plane that, for example, if this is 30 degrees, then we let this angle be 90 minus that, or 60 degrees. On this second, it works out exactly the same. Well, on the, let's look at this second one. There is an old exam problem that's similar to this. It works similarly. You set up your coordinate systems like this. Then you draw your force vectors. I have a normal force, Fn1, a weight, Fw2. On this problem that was from last year or the year before, I think, there was a frictional force on one of the surfaces. Let's call it Fk. It's going to oppose the direction of motion. We had this force, F. You have this force, Fw2, and then Fn2. And then you have a tension force. So you have a tension here, and you have a tension here. this angle would equal to this angle, and that was given on the exam. I'll just say its value theta. All right, this is ft, and then this is ft. So then you resolve your force vectors, and then you write your equations from Newton's second law. When you do that, you'll get a set of 4 equations, but you'll also need to figure out what is the friction on some of these. So for example, here you would have to calculate the friction by first finding the normal force. Okay? So your problem will look something like this. Do I need to set up the equations? Do you want me to set up the equations on these? Yes. Okay. I'm going to erase this inclined plane to give me some more space. If you get the equations on these problems, that's going to be the bulk of the problem, and you'll get most of the credit. However, remember, if you solve them by that Gaussian method, then you get 5 extra points. If you solve them by substitution, then you get full credit. So I resolve the vectors. Fn1, Fk, Ft cosine theta, Ft sine theta, and Fw2. And then over here, I have Fn2, Ft cosine theta, Fw2, get in right here. I have Ft sine theta, and I have the force F, which was given. Okay? So now in this problem, I gave you the masses of the blocks, I gave you the force F, and I give you the angle theta. And I also give you the coefficient. So I can just give you some values here. I'm not going to work out all the numbers, but let's just give some values. We'll say that mu k is 0.1, m1 is uh, 1, m1 is 2 kilograms, m2 is 4 kilograms, F, let's say, is 100 newtons, and theta was 30 degrees. So those would be your known values here. And what I want to know is, for example, what is the tension or what is the acceleration of this block? Those are your 2 unknowns, that you don't know the tension and you don't know the acceleration of the system. You would set up your equations starting up here. I'd say the sum of the forces in the y is Fn1 minus Ft sine theta minus Fw2. That's equal to 0 because it's in the y direction, not accelerating in that direction. And then the sum of the forces in the x direction is Ft cosine theta minus Fk. This is equal to m1, that's the mass of the block. This is for m1, this is for m2, times the acceleration. And then you do that for the second set of block, the second block as well. You say Fn2 plus Ft sine theta minus Fw2 equals 0. Those are in the y direction. And then the sum of the forces in the x direction is F minus Ft cosine theta. And that's equal to m2a. That's in the x direction. Yeah. This one right here? No, no friction on this one. Just because in the problem I say the top has friction, the bottom does not have friction. So see, I didn't list the force friction here. All right, just to make it a little simpler. But it's not an easy problem, as you can tell. There's lots of things that come into play here. And I'm not saying this is the problem that you'll have, but it's an example of a 2D two-body problem. Okay, so from here, The way you would approach this is you would say, um, let's see, what are your unknowns? You have to figure out your normal force. I think I might have to actually give you the tension in this to make it solvable. Uh, yeah, I'd have to give you the tension. So you would have to figure out what are your unknowns and your knowns here, and then solve the system of equations here. But it would have to be that you have to look and see sort of what you know and what you don't know. But in the system of equations, you would only have a couple of unknowns that you would have to solve for. All right? This is just an example. Look back at your old test. There's a real example with numbers put in, and you can work through that on your own. All right? But the process is going to be the same. You'll set up your two bodies with two coordinate systems, label all of your forces that are acting on it, and then solve the system of equations that you produce by Newton's second law. Okay? You with me on that? I can do that? Look back at some of the old problems. You might have an inclined plane. You might have one like this, but what you will have is you'll have two objects, one of which has forces that are acting off axis. Okay. All right. You will also have from chapter 5 a problem that was similar to like the ones we worked here, where I give you some object with some velocity, and you have to figure out the velocity or the height of it at other particular points. Okay, this would be a conservation of energy problem. Also, you'll have a force that varies with position. So say, for example, a force that's equal to 3x squared. And I ask you, in some way, what is the work done by that force as it goes over a certain distance? And the work is equal to the sum of F times dx, which in this case would be 3x cubed over 3, as it goes from 0 to whatever your x position is. Say if it acts over 3 meters, then it would be 3 cubed, or 27 joules. Usually the way I do this is I'll say that the object is moving at a certain speed, so it has a certain kinetic energy, and then it enters this place where this force is acting, and I ask how far does it move until it stops. And we work through an example like that in the class. So make sure you go back and look at that example. That's usually the way that I ask it. But look back at the old tests as well, what you would have to do is you would figure out the energy and set that equal to the work, and then set that equal to the integral of f dx. Okay? Just as an aside, this is really the integral of f. Don't write this down, but if you remember that our work is equal to f dot d, this is really the integral of f dot d. But we're taking the force and the position to be in the same direction, and so we just sort of get rid of that dot product. But the dot product is really there. It's just we don't write it because we assume that our force and our displacement are in the same direction. Yeah, Nicole. That would be a work energy theorem problem, or the work done by a position varying force, I think is what we called it in the notes. Okay, likely to have one of these. You're also likely to have figuring out the work due to a force where you have to do the dot product. I might just have this just as a separate problem, or it could be wrapped up in some other problem where I give you a force in vector notation, 3I plus 4j newtons. I give you a displacement in vector notation, 2I minus 1j newtons. And you have to figure out the work that's being done. It might have a k term too. But remember, on doing the dot product, you multiply the I terms, you multiply the j terms, you multiply the k terms, and they just all add up because they're scalar quantities. But you're likely to have a dot product on the test. Okay, you might also see conservation of energy with springs. For example, let's say I have a block of 2 kilograms at a certain height, say 3 meters. At this point, then, it has a potential energy equal to mgh. That would be 2 times 10 times 3. That would be 60 joules. And then let's say that it goes down onto a spring, and I ask you how far does it compress that spring. Let's say that K for the spring is equal to 10. What you would do is you would say the potential energy gravitational is equal to the potential energy of the spring. And so you say 60 joules equals 1/2 kx squared. This is very similar to the roller coaster problem, except now we're taking our potential energy here and converting it to elastic potential energy. So it's just adding in another term of our elastic potential energy. We worked through a couple problems with springs, so go through, or at least work through one, and there's some in your homework. Go back and look at this. But it works a lot like the roller coaster problems, except now we have another type of energy that's included. And here you would solve this for x. So 60, that'd be 120 over 10, be the square root of 12 would equal to x. Right, yeah, square root of 12 in meters. Okay? You could have something like that, or it could be wrapped up in the gravitational problem. Like, say, for example, I might give you a problem that looks like this, where the roller coaster comes down here, and then it compresses the spring, and I ask you, how much does it compress that spring? Or I could give you, and I've done this in the past, you'll see when you look at the old test, I could give you, down here, it just faces some force, and say that that force is equal to, or is dependent on position, of negative 3x squared, and you would have to take the total energy, and then I ask you, how far does it travel before it stops? You would take the total energy up here, 100 joules or whatever it is, and then set it equal to the integral of this function with respect to x, and then solve for x. I think we might have worked a problem similar to this, but look back and see in the old exams too. But likely you're going to have to integrate a function by the position to find the energy. Y'all can do that, folks? Yes? Okay. All right. So dot product, integrals. You need to know conservative, non-conservative forces, multiple choice stuff. Need to know when a force does positive work, when it does negative work. If they're opposite negative, same direction positive. That'll be in the multiple choice. Powers work over time. You may or may not see that. I'm not sure, but just know that definition is work over time. Although it is on your equation sheet. Make sure that you printed out your equation sheet. Don't bring it. You'll have the equation sheet on the exam, but print it out and just sort of, or look at it at least online, and make sure that you know what's on there and what's not on there. I think everything's on there, but just sort of be familiar with it. I think that's it for Chapter 5. In Chapter 6, we have collisions, and we have impulse problems. Impulse is delta F is delta P over delta T. An object runs into a barrier or whatever, it changes its velocity, and you can figure out what is the force that caused that change in velocity. Okay? You can tell these because usually only one object moves, whereas in a collision where you use conservation of momentum, you'll have two objects that move usually. And then also you can tell this because I asked for the force. And that should key you off that you need to use this Newton's second law written in terms of momentum. Second, you'll have a 2D collision. It'll be just like what we worked in class. So I'll give you two objects. I'll give you their masses, 1 kilogram, say, 2 kilograms, say. I'll give you their speeds in vector notation. So this would be 3I minus 2j. I'll give you all this. This would be minus 2I minus 4j. J. And then after they hit, what do? They go in this direction maybe. Let's say that this is negative 4I minus 3j, and then I ask you what is the velocity of this final particle. We did 2 examples in class. There's some in your homework and there's some on old exams. But they all work like this, and yours is going to look a lot like this. You have 2 objects. I'll give you their initial velocities. 2 objects. I'll give you one of their final velocities, and I ask you to calculate the final velocity of the second particle. Okay, so the way this would work is I would set the initial momentum equal to the final momentum. So your work would look like this. Pi equals Pf. I would say 1 times 3I minus 2j plus 2 times minus 2I minus 4j equals to 1 times minus 4I minus 3j plus 2 times Vf. This is the initial momentum of the first particle, initial momentum of the second particle, the mass times the initial velocity. This is the final momentum of the first particle, 1 kilogram, the mass times the initial final velocity, which is given, and then you solve for this. The only trick, it's not really a trick, but the only thing that you need to remember here is that you keep those I and J components together, because you can't add I's and J's together in the normal arithmetic way. You have to add them as vectors. But I'm not asking you to do that anyway. I'm just asking you to express VF in terms of in vector notation. So I'd say 3I minus 2j minus 4I minus 8j. Bring this over to the left-hand side, plus 4I plus 3j, divided all by 2, and then that will equal VF. Divided by 2 because of this 2 right here. When you combine your like terms, these cancel. Negative 10 plus 3 minus 7 halves j. And so that would be the correct answer in this case. That's the final velocity of the second particle. Very likely to have a problem like that. I'm pretty sure that you will. You also had the take-home portion that you'll need to turn in on Wednesday morning before class. And remember, I expect that to be correct. You can go in and check your answers. Just put in those numbers that I gave you for the initial velocities and the masses on some elastic collision calculator. If you Google it, the first one works just fine. Just put in the values and make sure that you get the right answer. But I'll be looking at your work, so make sure that your work is correct, that you substitute the equations properly, and that you do it correctly. Please do it perfectly so that it's easy for me to grade. And if it's not perfect, I'll count off a lot. It's not worth 10 points, that one. So make sure that it's perfect. That should be a good easy 10 points. Check your algebra really carefully. I think that's it for chapter 6. Yep, that's it for chapter 6. So what are sort of the burning issues for y'all? That's like this problem, right? Oh, for the take-home that you're doing? Right. Oh, for conservation of energy, you mean? Okay. Yeah, so you're not talking about the take-home. Because on the take-home, you only have kinetic energy. There's no potential involved. Uh, yeah, students often have trouble with that. So when you have a problem like that, you're likely to have one. Yeah, I've told you a bunch of problems, right, that you're not going to have all those. It'll be a normal length, 4 to 6. Because you have a take-home, each one will be worth slightly less, but it'll still be a normal length. Um, so on a question like this, let's say that I give you some object. Josh, this is what you're talking about, right? A problem like this. Say I give you some object. I give it a mass, or I don't even need to give you the mass, but let's say that the initial velocity up here is 10 meters per second. and that the height is, I don't know, 20 meters. All right, so what I like to do is I'll ask you the speed, say at this point, and then I might ask you how high does it go up here when the speed is equal to 0. What I like to do is to think about where is the potential energy 0, where is the kinetic energy 0. So I know potential energy equals mgh. So this equals 0 when h equals 0. So down here, for example, the potential energy will equal 0. And the kinetic energy is 1 half mv squared. So this equals 0 when what equals 0? When the velocity or the speed equals 0. So for example, up here, the kinetic energy equals 0. So that's the first thing that I do when I go through. And so here, I know it has what type of energy? Potential, but it also has a speed, so it also has kinetic energy. So it has both up here. I can calculate both of those. Down here, it only has kinetic energy. In fact, this is the fastest place where it's going because it only has kinetic energy. All of its energy is in motion right here, so it's the fastest. And here it has both. Because of the conservation of energy, I can say that the total amount of energy here, which is potential and kinetic, is equal to the total amount of energy here. Let's work that problem, and then we can find the speed. So if I say the total amount of energy, that's kinetic energy plus potential energy, that's from right here, is equal to the kinetic energy from down here, then I get this equation, 1 half m. I'm going to go ahead and put in my speed. That's 10 squared plus m times g times h, which is 20, is equal to 1 half m v squared. Then I can solve that for v. My masses all cancel. And I can solve that for v. The tricky part on these, like Josh said, is figuring out what type of energy I have at particular positions. All right, because sometimes you'll just have kinetic, sometimes you'll just have potential, and sometimes you'll have both. And you will need to discern that. But this is the questions that you need to ask yourselves. Is the height 0? If it is, it has no potential energy. Is the speed 0? If it is, then you have no kinetic energy. It's all in potential. Right? Likely to see a problem like this. It'll probably have some other parts wrapped up in it, like the integral, for example. But does that help a little bit with it? Yeah. I think before you had emailed me about that, right? Yeah, I thought you were talking about momentum. So those links that I sent you were not really correct. That was dealing with momentum, not energy. I know students have trouble with that. They get them sort of mixed up. But just be careful, as you're going through. Ask yourself, what type of energy does this object have? Nicole? Yeah, let's see. Where was that? I, Let me look before I answer that. It's chapter 6, 5, and number 7, you say? Yeah. Yeah, you could maybe do something like that. All right, part C there. Part C. Yeah, so this is a problem where you have this object that it gives you the mass and it gives you the height and it's initially at rest. So right here, it only has what type of energy? Potential. And it only has potential because the speed is 0. It says it's at rest. So I can figure out the amount of energy here. It only has potential energy. Ah, shoot. Let me save this so I can. That was chapter 6, right? It was chapter 5. Okay. Okay, so this object has a certain potential energy up here. I don't know what it is, but I'm just going to make up a number, okay? But you could find it. You can multiply the mass. Well, no, I'll do it right. So we'll say the mass, which was 100 grams, that's 0.1 kilograms, times G, which is 10, times H, which is 1 meter. So the total energy that I have up here is 1 joule. It has 1 joule of energy. Okay, and then at this point then, at h over 2, which is equal to 0.5 meters, the total amount of energy that it has is equal to zero point 0.5 joules. It's at half the height, so it has half the energy. Okay, so now I want to know how far will it travel up this incline in order before it comes to rest. And I tell you that the kinetic friction, the coefficient of kinetic friction, or the force due to kinetic friction, is equal to zero point 0.2 newtons. So Fk is equal to zero point 0.2 newtons. So what I know is that it's going to travel along this distance. Uh, oh, yeah, so you have to consider the height too. It's going to travel along that distance until it loses energy from the friction, and it gains potential energy until it reaches 1 joule of energy. So starting from here, where it has zero point 0.5 joules, it'll go up here until it has a potential energy plus the energy or the work done by friction is equal to zero point 0.5 joules. Um, so I'm not going to have you do this where you have to, you're dealing with two things that are increasing. The height is increasing, so the potential energy is increasing, and the distance over which you travel is increasing, so the work is also increasing. Not likely to have you do that, but what you would have to do is to figure out the work done by this force as it acts over a certain distance. Can I show you instead what you might see? So instead, likely what I would give you would be if this thing leveled out like this, and then you have a frictional force acting along this path, and I ask you, how far does it travel? You know how you would do that? Yeah. Well, I know that it has an energy of zero point 0.5 joules at this point. It has a kinetic energy of zero point 0.5 joules, and that's all going to be taken away by the frictional force, which is going to be the kinetic frictional force times the distance x. And so I'd say zero point 0.5 divided by zero point 0.2 would equal to x, which is equal to 2.5 meters. Look, it has 1 joule of energy up here. Down here, it has zero point 0.5 joules of potential energy. That means it also has zero point 0.5 joules of kinetic energy. Then it travels along this flat plane, and the kinetic friction takes away energy. For it to stop, it has to take away zero point 0.5 joules of energy. It's a non-conservative force. It takes away energy. And so the kinetic energy is zero point 0.5 joules. This is the energy that's being taken away, the frictional force times the distance, and then you solve for that distance. We did one more similar to this in the class, an example in the class. So yeah, Nicole, I wouldn't have you deal with this. You have two variables that are changing as you move through space. Not likely to have that on. Not going to have that on the exam. Is that clear? Y'all can work this type of problem. Not an easy exam. I think it's easier than the last exam, but not an easy exam. There is a lot of stuff on here. Some calculus stuff that we're beginning to see now more and more. The dot product, the integrals. Any other particular questions? Examples we want to work through? Not getting a very good vibe from y'all. Y'all feel ready for this test? Eh? Let's just look through some of the old exams and see if any stand out at you. Let's see. Let's look at exam 3. Okay, these are conservation of energy, and so here's an example, like I was telling you, where you go along. I ask you the speed of the cart at particular times. Here you would only have kinetic energy. Here you would have kinetic and potential. And then down here I have a resistive force, and you have to figure out what amount of energy does it have here, and then what distance does it travel before this force takes all of that energy away. What would you do with this force in order to find that distance? You would take the integral, that's right. You'd say the integral of 4x cubed dx, which is 4x to the fourth over 4, and then set that equal to the total amount of energy. Here, this is a dot product. I have a force that acts over a certain distance. Zoom in here. A force that acts over a certain distance. I ask you for the work, and you do the dot product. So you find the dot product here. What is the final velocity of the object? Once you do that dot product, work is equal to F dot D. That would be 20 minus 12. That would be 8 joules. Look, I multiplied these two numbers, I multiplied these two numbers, and I added them up. So I have 8 joules there, 4 times 5 minus 6 times 2. That energy now becomes kinetic energy. So for part B, I'd say 8 joules equals 1/2 mv squared, and solve that for V. And then finally here is encounters a spring. There's the spring constant, and I ask how much distance does it act? How much does the spring compress? So in this case, I'd say the 8 joules is equal to 1/2 kx squared. All that energy goes into the spring, and you solve for x. This is fall 15, exam 3, last year. I think this is in the back of your book, actually. Here's a 2D collision. This one's made a little easier because this speed is 0. So the initial momentum is negative 6I plus 2J. Then you set it equal to the final momentum, and you solve for V2F. Likely to have one of these, okay? In this case, it was worth 10 points. Yours are probably a little bit less than that, 7-ish points or so. Here I just asked for the difference between an inelastic and elastic collision. In inelastics, they conserve what? Inelastic collisions. Remember, the bouncy basketball is really elastic. It conserves what and what? Energy and momentum. Because a really bouncy basketball, you let it go, or bouncy ball, let it go, and it comes back up to you. Okay? It's an elastic collision. It conserves energy and momentum. But really, the only truly elastic collisions are those between what, chemists? Hmm? All right, a force field. Anytime I have an object that interacts by a force field, they don't actually touch. They collide, but they don't touch, so they conserve energy. You might not see it on the free response, but you'll see it at least in the multiple choice, or maybe in the free response too. Here, I'm asking for the average force, so that should key you off that I'm looking for F equals delta P over delta T. All right. My delta P is delta M times V over delta T. In this case, I have 25 kilograms. at 10 meters per second divided by 2.5 seconds. What this does is you have this water coming to the surface. The initial velocity is 10 meters per second. The final velocity, it says, is 0 because it falls straight down the wall. And so this is my delta V, this is my mass, and then this is the time. Just calculating the force. Again, this one wasn't worth very much, only 5 points, but, you know, they add up. Y'all could work one like this? It'll be similar to what you've seen in class. Looks like that was it on that test. Your test will look a lot like that, except you'll have the 2D, two-body problem. Okay? What else, folks? Any questions right now? I'll wrap it up, or do some more? Okay. Well, I guess we'll wrap it up then for now. But I'll be around if y'all have questions.